great. And as I mentioned, particularly Yasir and Subhro, for really taking care of people coming here and facing different aspects of Indian life. Excellent. So I will talk, perhaps you will find my lecture boring. I'm sorry for that, but this will be something that we need to go through. This is the basics, the basic ingredient of what we are later studying. The question is how the interactions arise between the magnetic degrees of freedom in materials. So we have very boring materials in the magnetic or electronic sense. Like, for example, this desk is not conducting electricity. This plastic thing is also not conducting electricity. It's just very boring, trivial. And the reason for that is that we know that all materials consist of atoms and molecules and so on. And in all those things here, we have a closed shell of electrons. They are somehow, to create some excitation, we need to invest a lot of energy. So these are, if you wish, these are Slater insulators in a more physical word. What we are interested in, and mostly me and some of you, is the Mott or charge transfer insulators. The charge transfer insulators means that they don't conduct electricity, but at the same time, there are some internal degrees of freedom which may interact among each other. And this interaction will give rise to many, many interesting phenomena that we didn't even dream of like 10 or 20 or 50 years ago. So let's start. Subhro told me that there will be, I asked, is there a blackboard? He said, yes, there's a linear blackboard. Fine. I didn't get what he means, but now I see this huge linear blackboard. This is great, because I'm not sure if I will be able to fill it. I think when he said that I won't be able to fill it, I thought, oh, he's joking. But I think I won't be able to finish it, to fill it all. But I have a serious question. If I write here, will you be able to see it at the back? So I will start, and if you can't, then you'll say, please write bigger. Okay, and I will try to write bigger. Maybe I start somewhere here. Yes, because this is long enough. And I started my career in 1D physics. So this should help.
We can start.
Okay, very good. Yes, perfect. Right. Okay, so insulators. So the question is, okay, may I assume that the spin algebra is familiar to all of us, all of you? You know, spin 1/2, how you deal with spin 1/2, the commutation relation, and so on. If not, then you may ask questions, or I don't know. And really, please ask questions. Interrupt me anytime. It's important. I have a list of what I want to talk. I'm not sure if I can go through everything, but I have a plan B and a plan C if I don't get there. Okay, so the question is that, okay, so usually what we have this, say, a crystalline solid or whatever, and there are different atoms. For example, we have these 2 atoms, and there are some degrees of freedom that are like magnetic ions. These are magnetic ions, and they are like spins. This magnetic ion originates both from the orbital part of the L of the moment of the electrons and the spin itself. Now, there is an interaction between those 2 guys. The question is, what is the interaction? What different interactions we can have, and how large it is? What is the sign of it? Is it ferromagnetic or antiferromagnetic? So if you followed electrodynamics course or just static magnetism, then you know that if we have 2 magnetic moments, they will interact with the dipole-dipole interaction. And the dipole-dipole interaction is something, I will call this a mu1, and I will call this a mu2. And is it visible? Ludo, can you? Good, okay, very good. So then the dipole-dipole interaction goes as follows. It is the mu1, sorry, I usually underline the vectors, but is it fine if I leave it underlined, or you would like me that I draw the arrows on top of the? Fine, okay, yes, good. So it is mu1 dot mu2, mu2, yes, divided by r to the cube, minus 3 times, and here's the unit vector pointing in the direction of r, mu1 times the unit vector pointing between, this r is just the distance between the two guys, I mean the vector, and here's the mu2. Perfect. So this is the interaction between two magnetic ions. If you put numbers in, you know now probably you know all those very strong rare earth magnets. It's a neodymium something. I forgot the precise composition. They are made of rare earth elements that have F electrons. F electrons have the largest magnetic moments of the atoms. In that case, and if you take into account the distance between them, in that case, for F electrons, the largest moments you can think of, and they are very close to each other, this energy is about 2 Kelvin, about 1 Kelvin. This is okay. For example, there are some materials that are called holmium, titanium 207. These are the so-called spinized materials, or dysprosium 2, titanium 207. In this case, the interaction coming from the dipole atom is about 2.3 Kelvin. It's very tiny, very small. In everyday life, we observe exchanges. Okay, everyday life, I mean physicists, not in the kitchen. So we see energies that are like 1,000 times larger. The effect interaction between the magnetic ions is about 1,000 Kelvin. So how do they arise if not by this dipole-dipole interaction? So let's try to look at the simplest model of Mott insulators, and that is the Hubbard model. Right. So what is the Hubbard model? We have two sides, and we have some orbitals on these two sides. It can be s orbitals, or p orbitals, or d orbitals, whatever you wish. And there's only single orbital per side. And then we can put either nothing or 1 electron. The electrons have spin 1/2, and they can point, say, up or down. So we can point a single electron, or we can put 2 electrons. If we put 2 electrons, then there will be the electrostatic interaction between them, and this will cost energy. So the Hamiltonian for the Hubbard model is the following. I will write, okay, and there is a small overlap between these two orbitals, so maybe I should, you know, I mean, they extend. There is some, let me use the colors. So this is one orbital, and then this is the other orbital. And there is a small overlap, and you can, and because of this small overlap, there will be a possibility for 1 electron on this side to jump over to the other side and vice versa. So to describe this process, we introduce minus d times, and then here I write C up, C1 sigma, dagger C2 sigma, plus C dagger 2 sigma, C1 sigma, plus the energy of interaction, which is and 1 up and 1 down. plus N2 up, N2 down. Can you still see this? I can't be, I need to see you if you can see. Is it okay still, the size of the letters? Not so. Okay, Ludo is saying that I need to draw it. Okay, so, right, so this part here, yes? Not smaller than that. Okay, fine, thank you. Yes. So this term here, U, is taking care of the electrostatic repulsion between the electrons. So if there are two electrons on one of the orbitals, it will cost you energy U. U is very large, it's about 10 electron volts typically. It depends on the type of the orbital and so on. The T, this is the hopping amplitude. This is the probability or amplitude that electron hops from one side to the another one, and this is also in the electron volt range. Harald is here. Harald is doing ab initio calculations, and probably if you are really interested in the numbers here, I think he's the right person to ask. Right. So what are the states? So we can have, I will use E for empty side. I will use sigma for a site occupied by a sigma spin electron, which can be pointing up or down. You see, I used here up arrow and down arrow. And I will use D for a doubly occupied site, which means that the two electrons are present. The sigma, okay, so empty, this is just nothing. The sigma is that I take the empty side and I apply the C dagger sigma operator on this empty side. And the double is I apply the C dagger up, C dagger down on the empty side. And these are fermionic operators, and they anti-commute. Because of that, it's important to know the order of these operators. And what we will use in the following, there are different possibilities, there are different conventions. I will site order them. We can use different, I mean, you may first choose to write the spins, up spin operators and then down spin operators. So these are my states. Is this fine with you? Any questions so far? Okay, very good. Now, what can happen? So let's try to apply the Hamiltonian, the state which I write like sigma empty. It means that we have a sigma electron on this side, and this second side is empty. So this is number 1, this is number 2. So what we do is that we apply, and this the Hamiltonian, the U, it requires 2 electrons. There is only 1, so it will not act. Only the T will act. And this is on side 1. So what will happen is that this one will eat an electron on side 1, and this will create it at side 2. So this matrix element will be minus T times C dagger 2 sigma, C1 sigma, applied to the C dagger 1. Okay, this is sigma prime, there's a sum here, and to the empty. Okay, and this guy will we can apply the anti-commutation relations for the fermions. This will be delta sigma prime sigma minus C dagger 1 sigma C1 sigma bar. So this is what turns out when we apply the anti-commutation relations. And this will be acting on the empty vacuum. I will put here 2 E's. So this is this here. And there's a C dagger 2 sigma prime, sum over sigma prime minus T times. This thing here, if acting on vacuum, will give 0. It will cancel out. So it means that the sigma and sigma prime needs to be the same. This is this term that is acting. And we will create a sigma electron on side 2. So this will be minus T times empty sigma. Okay. We can apply the same Hamiltonian to this guy. And then we will get that it will be minus T times sigma E. So we can write up a 2 by 2 matrix. So the basis is, and we don't leave this basis, it's empty sigma and sigma empty. And the Hamiltonian is just 0, minus T, 0 in this basis. This is fine. Does this mean not so? I started to learn what this means, but okay, yes. Because that will be on the next blackboard, next board. It will come, right? Okay, so that this is, I mean, we have no double interaction, no double occupancy. We don't have this 4 fermionic term. There is no interaction. So this is the non-interacting part. We can easily solve this. This is trivial. We will get 2 eigenvalues. We will get energies that are plus and minus T, and the corresponding eigenvectors are 1, 1 for the plus, and for the minus, 1, minus 1. Maybe I write it like this. Minus T energy equal plus T. And the corresponding wave function is empty sigma plus sigma E, and this is empty sigma minus sigma E. Okay, so this is that we see that we have a parity plus and parity minus solution for the single electron. Now Niels wants to know what happens if we have 2 electrons. So per orbital, so the U part is not acting. Can they hop? Well, they will be happy to hop, but this is already up, and it cannot hop because the other side is already up. So the energy, if we apply the Hamiltonian to this guy, it will give 0. It will do nothing. So this guy has energy 0. Similarly, we can apply, and the same holds for the down-down. Okay, good. Let's go further. We can have a situation where we have up and down. In this case, the up can hop to the side 2, or the down can hop to the side 1. And then there will be something going on. Let's try to work this out. So this is up-down. It is like C dagger 1 up, C2 dagger down, acting on an empty on the vacuum. Then we need to have the down up. And then here, when I said that there is a convention, here it comes into play, because you may write, like you may say that, okay, so let's write the upspin operators first. Or you can say, I mean, that would be like, and please don't write this in your notebook because I will erase it. So you could do it like C2 up, dagger C1 down, empty, empty. So this would be convention when you say that all the upspins are going first. Or we can use another one, and that is that instead of this, I will write C1 down and C2 up. Here, what I'm doing is I'm putting first the operators that are increasing in size. And these two conventions will produce a minus sign with relative to each other. To be consistent, it doesn't matter which one you choose, but you need to be consistent, and I'm choosing this one. Now we have the empty double, and there it is like C dagger 2 up, C dagger 2 down, empty, empty, and we have the double empty, and that is C dagger 1 up, C dagger 2 up, 2 down, C dagger 1 down, acting on the empty, empty. So this is the local Hilbert space, and we start to act the Hamiltonian onto this state. So let's do it. Hamiltonian acting on empty. How much do I spend with time? Okay. I 5 minutes. 25 minutes. Okay. H applied to the ED what will it give us? So it is H applied to the C dagger 2 up, C dagger 2 down, empty, empty, and it will be minus T times C1 dagger sigma, C2 sigma, plus C dagger 2 sigma, C1 sigma, applied to C dagger 2 up, C dagger 2 down, empty, empty, plus, I will continue here, U times M1 up, M1 down, plus N2 up, N2 down, applied to the C dagger 2 up, C dagger 2 down, empty, empty. Good. So this is how the Hamiltonian acts. Now, here we will have 2 electrons on side 2. So this will be acting this knot, and it will give us a U. Here, we will transfer electrons from orbital 2 to orbital 1. So this is not acting, and only this one is acting. First, it will act with the upspin, and then it will act with the downspin. Now, if we do this, let's write it out. It is minus T times, so C dagger 1 up, C2 up, C2 down, up, acting on this guy, C2 up, C2 down, dagger. I write EE at the, okay, I write EE like this. Then with the downspins, C dagger 1 down, C2 down, C2 up, C dagger 2 down, empty, empty, plus U times, this is diagonal, U times empty double. Yeah. Here I can do the the commutation, and essentially this will eat each other, and what will remain is that I will move the upspin from side 2 to side 1 minus T times, maybe I do it slowly, C dagger 1 up, C2 down dagger, empty, empty, it's fine, plus here, this is the annihilation operator of downspin, and the other one is here. there is another fermionic operator in between them. So if I move this C annihilation operator next to the creation operator, I will cross the C dagger and it will give us a minus sign. So I need to change this plus to minus. And I shall write C dagger 1 down, C dagger 2 up, acting on empty empty, plus U times empty double. Happy? Good. So it will be minus T times up, down, plus T times down, up, plus U times empty double. Okay. So we can write the first column in our 4x4 Hamiltonian that looks like follows. So this is a Hamiltonian in the 4x4 basis. It will be U, and my elements, I mean, but I use the convention that the basis is empty double, then it is up, down, down, up. This is the Hilbert space, double, empty. Right. So there will be a minus T, there is a T, and there is 0. So this is the first column. Now, we can continue, and then if we continue, we will end up with the followings: 0, 0, minus T, then T, 0, 0, T, and 0, minus T, T, U. So this is the 4x4 matrix that we need to solve. Okay? Good. Subhro, look, I almost filled the blackboard. Yes. Okay, so is this a hard wall?
It's the Berlin wall. You can make it.
What? Okay, camera cannot follow me anymore. Okay, so let's go there. Yeah. Okay. Very unfortunate. Yeah. Okay, so okay, I will copy this matrix there. So U minus T, T, 0, minus T, T, 0, 0, 0, 0, 0, minus T, T, U, and minus T, T. Okay, this is the matrix. So let's try to find the eigenvectors. It's clear that if we choose 0, 1, 0, 0, minus 1, that this is an eigenvector, right? Because if you act with it, this will give U, this will be 0, 0, minus U, so the energy of this guy will be U. And this is empty double minus double empty. Okay, good. Similarly, I can use 0, 1, 1, 0. This is another eigenvector. It will also have it will have energy equals 0, because it will, I mean, if we multiply this vector with the matrix, it will give 0 here, because it will minus T plus T is 0, here nothing, and again nothing, so we will get everything 0, so this is eigenvector with eigenvalue 0, and the corresponding states are up, down, plus, down, up. Very good. And let's stop here for the moment. Here, already we had some guys that have zero energy. The up, up, and down, down, they have zero energy. And we found a third one that also has zero energy. This guy here. So there are three states that have zero energy. This guy, and that guy. So up, up, down, down, and up, down, plus down, up, they all have zero energy. And these are nothing else but the spin, the total spin of these two spin 1/2 of this state is spin 1. You apply the SZ for these two sides, and then you will get 1/2 plus 1/2 is 1. And they really belong to the S equal 1, the triplet representation of two spin 1/2. Is this fine with you, please? If somebody, I can explain it in more detail if needed. Okay, nobody is saying no. So they make a triplet, spin S equal 1 triplet. Very good. Now, this is some other guy. And then there are still two eigenstates that we need to take care of. They're a little bit more complicated. And I need to delete starting point. The eigenvectors are not normalized. U plus minus U square plus 16 t square minus U minus plus U square plus 16 t square and 4t. The corresponding energy is U over 2 minus plus square root U square over 4 plus 4t square. This is a little bit more complicated. Let's try to draw the energy levels of this problem. This is the single particle. In the single particle, we found two states. One is having energy minus T, and the other is having energy plus T. So if there is no interaction, we will have these two energy levels. I think I will just come here. So here we have the energies, and here we have the U over T. So this is strong interaction. If it is 0, it is no interaction at all. And for the non-interacting case, we can use the single particle picture. We have two orbitals. The two orbitals are the minus T1 and the plus T1. Now, we can put two electrons on the lower one, on the bonding one, and this will be energy minus 2T. And I don't want to, let's see, I have a red color. I have a, yeah, very good. I have colors, this I will use. So, here I have minus 2T, and this will correspond to filling these two orbitals. Maybe I was not, let's do it. Let's do it differently. So there is a plus T minus T level, and we put up-down electrons to the lower one. It will be the 2T, minus 2T energy. Then we can put the up spin, down spin on the on the antibonding and bonding orbital. In that case, the energy would be 0. Or we can put both electrons onto the antibonding orbital, like this here. In that case, the energy will be 2T. This is only one possibility to do this. So this is one-fold degenerate. Here, it is also one-fold degenerate. We can do it only one possible way. And here, we put the up and down. We can choose whether we put the down here, up there, or maybe we put down here, and so on. So altogether, there will be 4 states at 0 energy. Right, 4 times degenerate. Okay, these guys here are singlets. So here, I mean, because we have an up, down, they if we apply the spin raising operator to this animal here, we get 0. So this is definitely a spin 0 object. This is also a spin 0 object. So these two are singlets. And here we can have an S equals 0 or S equals 1. S equals 1 will be something that we encountered here, is up, down, plus down, up, and I think, yeah, and then these guys. Okay, so this is what we learned from the non-interacting case. Now let's draw what happened for finite U. The triplet continued to have 0 energy. So the triplet continued to have 0 energy. These are these guys here. Then we had a state that I think I deleted, that was empty double nodes here, where the empty double minus double empty is just having energy U. It is because that the interference, that if we want to split the double, it will produce a double up, down, down, up, just the opposite sign with this guy. So the delocalization doesn't play a role here. So energy is equal to U, and that I will use a different color. Maybe I will use the blue. And the blue is going up linearly proportional to U. So this is the empty double minus double empty. Okay. Here we have the up, 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 down, minus down, up, and the down, down. Okay. And then what remains are the... Thank you. Yes. And what remains is this energy here. If we draw it, you can use your favorite plotting program. It is something like this and something like that. Right. It will approach from below this energy 0. So let's look at this one. So this energy is, we need to use the minus sign. So this is U half minus square root U half squared plus 4T squared. This is the energy of this guy. So because here we have U half, and we have the same thing squared plus some quantity, positive quantity. So this will be larger than U half, so this will be negative. This will be always below. We can expand this in for large U, and then this will become minus 4T squared over U. So there is an energy difference between this yellow level, that is a singlet, and this upper level, that's E equals 0 level, that is a triplet. So what we get a splitting between the singlet state and the triplet state, which has energy minus 4T squared over U. And in fact, this is the origin of the exchange interactions in Mott insulators. Right, so let's try to be more specific, but before that, let me also try to write you the wave function in the large U limit. It will be up, down, minus down, up, and plus 2t over u. I'm expanding the wave function that is over there. That's 2t over u times empty double minus double empty. Is it right? Maybe plus? I think I need to write here plus. Sorry. Okay, so what it tells me that it is not pure, the wave function is not only composed of a single occupied size, but there is a mixture of charge fluctuating part. So there will be always some double occupied sites in this wave function. And this is very important. So if you have a Mott insulator and you apply some probe that is interacting with the charge densities, you will be able to see this part. And you will see signature of these charge fluctuations in your dynamical spectra that you are measuring, like EELs, this is electron energy loss spectroscopy. To take into account these parts is important. So what do we learn here? Okay, so let's first, let's write the effective Hamiltonian, and then we will discuss what happens. So how to write the effective Hamiltonian? So we have two spins. This is a triplet, this is a singlet, and the singlet is lower in energy. So I can write the H effective equal to 2t squared over u times s squared total minus 2. The s total for the singlet is 0. So this will give me minus 4t squared, which is this energy. Okay? Right. If we act what is the s total square of the up, say, the triplet, it will be equal, this is a spin 1, so it is s times s plus 1, it is 2 times up. So this is spin algebra that I hope you know. So in that case, if we apply this Hamiltonian to the up, we will get a 2 minus 2 is 0. So this effect, H effective applied to the up will give 0. Let's expand this. Is it fine? You get the idea? Please nod if you don't. Okay, so what I want to do, right, so what we know, what we learned so far is that here we have spin eigenstates of the total spin, and they are spin triplets. This guy here is essentially a spin singlet, s equals 0. So they are both eigenstates of the total spin operator. So the S total operator is just defined, I mean, like alpha component of the S total is just sum over alpha, S1 alpha plus S2 alpha. So this is the total spin operator. And it knows everything what it shall know about the SU2 algebra of the spins. And if we apply, for example, SZ total to the up, it will give us 1/2 plus 1/2 is 1 times up. So the SZ total of the up is just 1. If we apply the SZ total to the up-down plus down-up, it will give us plus 1/2 minus 1/2 gives 0. So this gives 0. So this is the SZ equals 0 part of the, we don't know if it is a triplet or not, but if we apply the S plus total to the up-down plus down-up, it will give us up with a coefficient that I am not pretty sure of. So there will be some coefficient here, the proper one, I haven't used here, I didn't normalize the states, blah, 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 so I'm not sure about the coefficient here, but nevertheless, we will be able to raise this SZ0 state into this state here. So it tells us that the up, 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 down, plus down, up, and the down, down, and the down, down, minus 1 times down, down, that they are part members of the S total equal 1, SZ equal 1. This is the up, up, S total equal 1, SZ equal 0 is the up, down, plus down, up, and with the minus 1 here is the down, down. And we have the up, down, minus down, up. If we apply the SZ operator to this guy here, it will be 0. And if we try to raise it, if we apply the S plus total up, down, minus down, up to this guy, what will happen is that we try to to move the downspin to upspin, because that is the spin raising on side 2. It will be up, up, minus, I want to raise the downspin here. It will be also up, up, and the 2 will cancel. So I cannot raise this state anymore. And if I cannot raise it anymore, and the SZ is equal to 0, this guy must be a singlet. Is this fine? Or getting clearer? Okay, so what we know that these states are eigenvalues of the total spin operator. So if they are eigenvalues of the total spin operators, eigenstates, in that case, we can write the effective Hamiltonian, just that this total square that acts on these states, and it will produce as diagonal elements, and they will produce as the 0 and the minus 4t squared over u. So if we have this Hamiltonian, and we act with this Hamiltonian to a triplet state, then the S square total acting on the up, up will just be 2 times up, up, because the S square, either you calculate it, or you know that the S square of some spin, of some S spin, will be S times S plus 1, the same S spin. So we use this fact, that if we apply the total square of a spin, total square of the spin operator to a triplet or singlet, we will multiply the state by S times S plus 1. This is coming from the spin algebra. So this is what I wrote here. Yes? Yes? It's charge fluctuation because if we can ask what is the expectation value of the charge in this wave function. The expectation value of the charge will be just 1. There is only one, on every side, altogether we have 2 charges per 2 sides. But if we ask what is the expectation value of the n square, and look at the fluctuation, n square expectation value minus expectation value squared, it will give a finite value, and it will be proportional to this d over u, d squared over u squared. Right. So, okay, so is this okay now? Yes. Yes, it is only for very good question, very good remark. This guy here is the effective Hamiltonian for these 2 levels here. Yeah, H effective. That's correct. We are only describing these 2 levels here. Yes, it will. It will. And there is also a t squared over u contribution here. And that is a different story. There is a larger algebra that can be associated with the Hubbard model. Right. Okay, so if this is the Hamiltonian, let's work on this a little bit further. So S squared minus 2 do I go? Let's just go here. So the H is 2t squared over u, s total square minus 2. This is the Hamiltonian. I expand this 2t squared over u, and here, this is like s1 plus s2. Okay, so these are operators squared, and this will be 2t squared over u, s1 squared here, plus 2 s1 dot s2 plus s2, I shall write bigger, s1 squared plus 2 times s1 dot s2 plus s2 squared minus 2. I'm just rewriting this full square. If we apply the s1 square to spin 1/2, then the s times s plus 1 for spin 1/2 will give 3/4. 1/2 times 3/2 is 3/4. So this here is equal to 3/4 plus 3/4. So this here is equal to 3/2, 3/4. We have two of them, that is 3/2 minus 1/2. It will be minus 1/4, minus 1/2. So this is equal to 2t squared over u, 2 s1 dot s2 minus 1/2. And here maybe this is okay, like this. So this is the effective interaction written using the spin operators on side 1 and side 2. So what we learn, and one can calculate what are these numbers here. We have electron volts and we have electron volts. So this can be very large. This can be electron volt, and 1 electron volt is 10,000 Kelvin. So from this process here, the fact that there is a Pauli principle, and we cannot put two upspin electrons on a single side, but instead what happens is that we have this, the downspin, which makes a singlet, visiting the neighbor. Of course, it will pay some energy, but the ability to visit the neighbor and come back, that is what will give rise to the exchange interaction between the magnetic ions in a solid. You also see here that in the beginning, we had here the dipole-dipole interaction, which was something like S dot S, that was a isotropic part, and there was another term that was the R dot S times R dot S, and that is anisotropy. So that Hamiltonian, the dipole-dipole interaction is not isotropic, but this guy is. This is an isotropic exchange. So whenever we don't have something that is called spin-orbit coupling, that I was hoping and still hoping to be able to talk in the second lecture, the effective Hamiltonian is isotropic. It doesn't know about the details. I mean, the spin rotations and the real space rotations are yet decoupled, right? Okay, so do you have any questions now here? Okay, good. Yes. Sorry, I can't hear you acoustically. Just shout, please. Yes. Yes. There is one word that I don't understand. So here, what we do is that we put, there is a minus T level, and I can put up and down there.
Yeah,
Yes.
But then you are telling this is non-interacting case.
Yes, this is a non-interacting case. That's right.
So, but
because U is equal to 0, I'm here.
Okay.
Really here, this is a U over T. At U equals 0, they don't talk to each other. if you look at what is this wave function, you need to, there was this up, down, plus down, up. You need to check what is this, and if you expand this wave function, you will see that it will be like having components that you have a single electron, one electron on one side, another electron this side, and it will have equal probability of having 2 electrons on one side. Right. And that will lose energy later. Yes.
So you have taken only 4 plus 4 never
I think he must, okay, so here I had 1 state, here I had 1 state, and here I had 4. So,
in metric form.
yes.
You have taken 4 plus 4.
Yeah, because I was, I neglected the up, because, yes, in this matrix, there are also the, I mean, if we take into account 6, there is another 0 here and 0 here. This is the up, down, down. Yeah, right. Okay, good. Yes, yes. 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 Here I was talking, this is just the effective model. And if you do expansion, very good. Thank you for this question. If you do the expansion in t squared over u, t over u, only the nearest neighbor, those states, those sites will contribute that are connected by a single hopping. Further hoppings will contribute in higher order of expansion. And maybe I will be able to talk about how do I stand with time. It's very bad, isn't it?
It's like an hour.
Over.
Yes.
Oh, and 20 more minutes.
Yes.
Yeah. Okay, yes, good. Excellent. So, this was kind of troublesome. We had the square roots and so on. Can we derive it differently? Let's try to get some physical picture. And let me raise this until here. So, we can do perturbation expansion. Starting from U large limit. If U is large, then the low-lying states are the spin states, up, down, up, down, up. Let's see, suppose that we start from the up, down. What can happen? Well, what can happen is that we can hop this up electron to either side 1 or vice versa. Then there will be, and what this axis is here kind of the energy. So this is kind of 0, and this is kind of U. Okay? So we can hop with a probability minus t to the double empty. And this double empty can hop either back here or hop or exchange the 2 spins so that we get down, up. And this will be probability t. This is what we calculated, but you can get it differently. Similarly, there is a minus t probability that we go to empty double, and it will connect with t to these guys here. And we know that in perturbation theory, second order perturbation theory, the energies are given by, here we have like a ground state, Hamiltonian, excited state X, H, here again, ground state divided by energies, Ax minus A naught, okay? This is a little bit hand waving because what we are doing is the general perturbation theory. It's a little bit more involved mathematically, but essentially this is it. What we want to do is that we will have an effective matrix element that will connect this state And the value of the effective matrix element is the transition probability, T, divided by the energy, U, and transition is 2 times, so it is T squared. And what we end up with is that that we can write something like this. There's an upspin, downspin, downspin, upspin, and there is a 2t squared over u probability coming from this expression here of the second order perturbation theory. Yeah, maybe there's a minus sign here. That will connect these two spins. If starting from up down, I hop to one of those, I can also come back. That will be, I will just draw it with this arrow, that this has some self-energy that is minus 2t squared over u. And here, the same thing here, minus 2t squared over u. So these are the processes where these red arrows come from a second order perturbation theory from the fluctuation part. Okay? Excited, virtually visiting a double occupied site. Then we could write that this effective Hamiltonian is two t squared over u p12 minus 1. Okay, so now you see something new, this p12. What this p12 means is that it will just transpose or swap or permute the states that are on side I and side 1 and side 2. So this is just a permutation operator that will take, or exchange operator if you wish, that will change up down into down up here. And let's see how does this work. So in case that we apply it to the up down, we get down up minus up down, and those are those coefficients, that amplitudes that I have written here in the red. And this thing here is precisely the same thing what is written here. You can check, if you wish, the homework, that if you apply the S1 dot S2 times 2 to spin up down, and you subtract this minus 1/2, you will get precisely this operator here. This only works for spin 1/2. Okay, for spin 1 it does not work. Right. Niels had a question. What happens if the lattice is more complicated? What can happen in that case is that maybe we don't stop at the second order perturbation theory, but we do something else. Right. Suppose we have a triangular lattice. And we are not working with electrons, but we are working with helium-3. And these are the top layer of a helium-3 on a graphite lattice. The helium-3 electronic shell of the helium-3 is closed. Only the magnetic degrees of freedom are the nuclei. The nuclei have spin 1/2. What can happen in this case? What can happen is that, for example, we take an atom A and B, and somehow they move in real space and then somehow exchange themselves. But this costs a lot of energy. It's much easier to have like a ring exchange when this hops here, and then the other guy hops here, and then hop here. You see that somehow there is a reconfiguration of these guys, and they just rotate around each other. Or maybe they can also take 4 spins, and they can rotate. This goes here, this goes here, this goes here, and this goes there. So these are so-called ring exchanges. in that case, the effective Hamiltonian can be conveniently written using the Pij's and Pijk's and Pijkl, where, for example, this Pijkl means that this is Ijkl, that the spin hops from this side to this side, from here to here, from here to here, and back. Right. And these terms were important to understand the physical properties of helium-3 on a graphite. They will lead to spin liquid-like properties. It will not order. If we are dealing with spin 1/2, it turns out that this guy, if we look at the P1, 2, 3, and we also need to have the Hermitian conjugate, which is 1, 3, 2, that this does not exist in the sense that it will be decomposed into P1, 2 plus P1, 3 plus P2, 3. And there is a number here, maybe -1. Sorry, I am not, I think probably it's fine. So that if we act on the spin 1/2, then this will contribute to the two-side exchanges. So the effective Hamiltonian will be 2 sides and 4 side exchanges and 6 sides and so on. But the 5 sides, 6 sides, and so on. Another example is the lanthan copper oxide. Maybe I delete this here. Yes.
So it's not, I mean, so the spin is the Subhro spin. So I mean, it's the occupancy of the helium itself that you're.
Yes, but the spin goes with it.
That's right, but it's not the exchange of the spin of the helium in the nuclear.
What is the difference? I mean, your atom is characterized by the spin that is inside. I agree, your distinction shall be made, but essentially we end up with the same thing. But Yogesh is right, we are exchanging atoms. It's different from what we did here because the atomic orbitals were staying on side. Lanthan copper oxide, and I need to put some numbers here, and I hope I will get them correctly. Okay, LAN2. Now, can one help? What? Okay, 2, 4. Yes, 2, 4. Good, excellent. This is a square lattice of copper d orbitals and the oxygens, and like this. Maybe I use green for oxygens. And what happens in this material is more complicated. We will have something that is called super exchange, and we will have something also that the ring exchange part will come into role. So far, we discussed the Hubbard model. Hubbard model, 2 sides, and there is a direct exchange. There is a hopping from one side to the other side. But in the lanthan copper oxide, the spins are sitting on the d orbitals of the copper. Here are the spins. And there is in between the oxygen d orbital. So if we are to draw a perturbation expansion, in this case, it would be more complicated. How will it look like? So what we start with is, okay, so this is not precisely in a more strict sense, this is not a Mott insulator, this is a charge transfer insulator. What does it mean? Certainly, there is a U for 2 electrons on a single copper side, but there is a smaller gap when the electron hops from the copper to the oxygen level. Then the energy will be the difference between the chemical potential of the copper D and the oxygen p orbital, and that is the so-called charge transfer gap. Let's see what happens in this case.
Karlo,
Yes.
I have a question. So what is the lowest energy experiment that can tell the difference between a Mott insulator and the charge transfer
APES,
insulator?
then,
APES.
yeah,
I see.
APES, you will see very clearly, I think Zawadzki group, they were working a lot trying to figure out precisely what's going on, how it goes, and so on. Yes, or some experiments like electron energy loss spectroscopy.
But as far as the spin physics is concerned, I can.
You are ignorant. Essentially, you are ignorant.
Okay.
Whether it's coming from charge transfer or whatever.
Okay.
Yeah.
Thanks.
What did I do wrong? 214. Thank you, Howard. Yes, I knew that something is fishy. Yes, there was a question.
How do you distinguish, like, what is the difference between Mott insulators when you turn on this interaction? Because of the interaction, it goes into insulator.
Yes, so perhaps I shouldn't have mentioned this because it is just it depends how you deeply want to dig into the properties of materials. But I mean that the difference is that you look at we can look at the energy spectrum of this guy here, forgetting the spins. And then what will happen is that you have the lowest state is where the electrons are all sitting on the copper. Then what can happen is that there are also other states where, for example, electrons sitting here. I'm looking at the diagonal part, no hopping, nothing. You can put electrons here, a single particle picture like no hopping. Then you can put one electron here on the p orbital, and then what you will see that there will be, okay, so this is, the ground state is that all electrons are sitting on the copper. Okay, let's yes, let's do it this way. Yes, very good. So this is the, I just write, yeah, just two coppers and an oxygen. Right here. So if there is a one spin and let's call this like sigma empty sigma, and the middle one is the oxygen, okay? So this will have energy that is essentially zero. If you have something like empty sigma, so you moved, let it be sigma prime, so you moved, you occupy one of the p orbitals and one of the d orbitals, then the energy will be something that is the epsilon of the p orbital of the oxygen minus epsilon of the d orbital of the copper. And S square minus, okay, you don't see this. And this is so-called the charge transfer gap. Or you can have the situation where these are empty and you will have up-down on the copper side. And here the energy will be just U. And depending on whether the charge transfer, you can draw a picture here that you have this is a single occupancy, and whether the next one is a charge transfer here, and then higher energies are the U, or first U and then charge transfer. That will characterize whether you are talking about charge transfer or a Mott insulator. So if the lowest excitation is from copper to the oxygen, then the smallest gap is this charge transfer gap.
Unlike Mott insulator where there's 2U or U.
Yes.
Here there is another gap.
There is another gap, precisely. Yes, right. Okay, so starting from this, actually this was useful. So we can also try to figure out what happens. And then we can also try to write a perturbation diagram like what we wrote over there for the Hubbard model. How will it look like? It will be more complicated. Yes.
In either case, the picture that you have drawn of glass transfer gap was U. In either case, the system is a Mott insulator. Because if there was no U, then what I'm saying is,
Yeah.
even if the delta.
Yes, yes. We need you to. Precisely. Yes. Thank you. Thank you very much. Yes.
Mott insulator in any case.
Yes. Yes.
Except
Yes.
that the spectroscopy will see either the gap between the Hubbard band and the oxygen mole, or the Hubbard band and the upper Hubbard.
Yes. Thank you.
But it's
Yes.
a Mott insulator nevertheless.
Right. Okay. So, Okay, so we have the copper, oxygen, copper, and we start from this here. Upspin on copper. How much time do I have, Subhro? 5 minutes. Okay, 5 minutes shall be enough to get this right. Okay, so we have the two occupied copper orbitals. Oxygen is empty. There is a hopping that will move this electron from copper to oxygen. Then we have some excited state. And it will look like this. Okay, we moved it to the p orbital of the oxygen. So this is the green. This is the p orbital of the oxygen. Right. We could have moved also the other one, but let's keep things simple. Then here, I can continue. I mean, of course, we can come back, but there will be two possible choices. Either this guy is hopping further, visiting the other electron on the other copper side. That will be like double occupied copper side and empty p orbital, or the other copper spin will hop to the oxygen side, and there will be two electrons on the oxygen side. So this is it here, and we have it here. So this will be two electrons here. And then we have the possibility that the downspin goes here, the upspin remains at the oxygen side and empty here, and eventually we end up with spins that have exchanged their position. So this would be, is it okay? It's going, so this is the state, initial state, this is the final state, and these are the intermediate states. And half of them are missing. So this is the hopping amplitude is TPD, usually people call it TPD. The energy here is just the charge transfer gap here. The energy here is also the charge transfer gap. Here, this is the 2 times charge transfer gap plus U of the p orbitals, which is usually negligible. And here we have the U of the copper. So these are the energies of these diagonal energies of these states, if hopping would be 0. Right. And then we can again collect and work out not second order perturbation theory, but fourth order perturbation theory. It's a little bit more involved. But what we end up with is the following. So definitely we will have one, here's another TPD, here's another TPD, and one more TPD. So this will be TPD to the 4th power. So the effective exchange is J is proportional to 4 TPD. I mean, the 4 comes from counting the pass. And we have the first intermediate state is the charge transfer gap energy. So this is charge transfer. We have it at the beginning and the end. So that's why we have delta charge transfer to the square, because this one of the T square PD over delta corresponds to this state here, and the other corresponds to here. And then we have the intermediate state, and the intermediate state, which is, I mean, the highest energy, or in the very middle, is either 1/u of the d orbitals, or 2 times this guy, 2 delta charge transfer plus up. So this would be, in lowest order, the exchange interaction in lanthanum copper oxide, and this is called super exchange process. It's just a name. Right. And it turns out to be, for example, in some of these materials, like I have the value for the strontium copper oxide, for the strontium copper oxide 2, 3. The J will be, this is a linear spring material. The J value is 2200 Kelvin. So this is coming from this type of processes here. Okay, about 1000 times larger than it was the dipole-dipole interaction. Okay, yep. In this, so you see that what we did was to go to oxygens. What also can happen is that this electron starts to propagate and move. It goes to oxygen, it goes to copper. Instead of going to this oxygen, it continues here and goes here and here and here and here and comes back. That would be the 4th order or 8th order or whatever order ring exchange. Now it turns out that for this particular material, if you look at the neutron spectrum, to be able to explain the details of the neutron spectrum, it will be essentially be an antiferromagnet. One would needs to include this 4-side ring exchange, and it will be roughly, I forgot the precise value, but it will be roughly between 1 and 10% of the J 2200 Kelvin, 1000 Kelvin. So it is appreciable, it is observable, 4-side ring exchange. Okay, I think I shall stop here. This is a good point to stop. And I think I will need to, it's already plan C, what I'm doing now. Yes, thank you.
Thanks, Karlo. Some immediate questions, more questions? Actually, okay, yeah, please go on. Use the mic. Just use the mic.
Are you considering all the d orbitals degenerate? Like you're not taking the different d orbitals?
Very good question. Please come back for your next tutorial. Yes,
you had
perfect.
a question.
They are degenerate. They are not degenerate.
I would like to know about the helium structure on a graphene.
Yes.
So you mentioned one thing. If there is
a graphite. This goes back to 30 years or whatever. I mean, it's old stuff. They didn't have graphene yet. Graphene would be the single layer. They just put it onto the graphite. Yes.
So I would like to know, you mentioned one thing, it could be possible that if there is a ring exchange over a triangular structure,
yes.
there could be a spin liquid
yes.
you mentioned. So I would like to know about that. So how that ring exchange process?
Okay. This is right. So it's a non-trivial thing, highly non-trivial thing. I mean, I would not like to enter here. The simplest thing is that what this exchange interaction does is that it will just order antiferromagnetically. Then the next step is frustration, when instead of having a usual antiferromagnetic up-down, you have like a 120-degree order and so on. And if you go further and further, then these ring exchanges will start to play and will give you this sort of long-range order. And to show that this is really a spin liquid, you need to have very elaborate techniques. Like okay, so there were pictures like RVB, resonating valence bond, that is essentially what it was a counterpart of the ordered state, and it connected like spin up and downs into one thing.
That is what 2.8, right? That is S1 antiferromagnetic exchange. But this ring exchange that
Yes.
you said like this,
Yeah.
PIJK, those processes. So that I did not understand how that could.
I mean, what it does is that it will really mix up your wave function. I mean, if you have like a, I don't know how to answer this question. This is a difficult question. I mean, like, Subhro, do you have a good answer to this?
Not at this point.
Not at this point. Okay, he's saving me. Right. So it's really non-trivial why ring exchanges. I mean, what people do is really they look at the exact. I mean, you really need a very careful study of the systems, and this is a strongly correlated interacting system. A solution is not simple, and you need some different techniques and try to figure out what is the ground state, and maybe right. I'm sorry. I think this goes well beyond the, but maybe I don't know. Yasir is also he's hiding there. Can you talk to the microphone, please?
Yeah. But with this ring exchange process, that is something new for me, and I wanted to know how this could lead to such.
No, ring exchanges are also frustrating exchanges. On the triangular lattice, they could also realize, they could also melt long-range magnetic order of the 120-degree type. And you could realize a state which has no long-range dipolar magnetic order. And there have been studies trying to propose.
It's going on for 20 years, 30 years, 40 years.
Okay.
So did this helium-3, they got a Nobel Prize for this thing. So it is going on for like, what is this, 70s, 80s maybe, 80s. And when people try to look at this ring exchange, how to calculate it with Monte Carlo, that is from the late 80s.
Okay.
Like Zeppeli and, yeah.
Okay, yeah, I'll look into it, yeah. Thank you.
Yes, I'm sorry that I cannot provide a more detailed answer at this stage.
More questions? Is there any question from the online participants? You can unmute yourself and ask the question. We would be able to hear you. Okay, doesn't look like. So let's thank Karlo for part 1. And so we gather like 10 minutes to 12 and have Karlo's part 2. Okay. Yeah.
And the tea and the coffee are just served in the foyer, just on the right.